I had a dream once, a dream so simple yet so revolutionary that it shattered everything I thought I knew about reality itself. Picture this. You're trapped inside a windowless elevator. No buttons, no escape, just four metal walls closing you in. Suddenly you feel your feet pressed firmly against the floor. Your body feels heavy, substantial. The question that will haunt you is this: are you falling or are you standing still? This isn't just a puzzle. This is the thought experiment that broke physics, and I'm going to show you how this simple elevator revealed the most profound secret about the universe. A secret so disturbing that even I struggled to accept it for years. Let me start with something that should terrify you. Right now, as you sit reading this, you cannot tell whether you're accelerating through space at incredible speeds or simply resting in a gravitational field. The feeling under your body, that pressure, that weight you think is so familiar, it might be a complete illusion. I remember the exact moment this realization hit me. It was 1907, and I was sitting in my office at the patent office in Bern. The morning sunlight streamed through the window, casting long shadows across my desk. I had been wrestling with a problem that tormented me, a flaw in my own work that I couldn't ignore. You see, I had just published my special theory of relativity 2 years earlier. The world was beginning to accept that space and time were relative, that nothing could travel faster than light. But there was something wrong, something that made my stomach twist with unease every time I thought about it. Gravity didn't fit. In my theory of relativity, I had shown that all motion is relative. There's no absolute reference frame, no universal standpoint from which to measure movement. But gravity seemed different. Gravity appeared to create a preferred reference frame, the one where you're addressed with respect to the gravitational field. This contradiction gnawed at me like a physical pain. How could gravity be special? How could it violate the very principle that I had worked so hard to establish? That's when the elevator came to me. Imagine you wake up inside this elevator, but you have no memory of how you got there. The floor presses against your feet with exactly the weight you remember from Earth. Your pen falls to the floor at the same rate you always observed. Water pours downward in the same familiar arc. Now here's what should make your blood run cold. I can construct two completely different scenarios that would feel identical to you. Scenario 1. Your elevator is sitting motionless on Earth's surface. Gravity pulls you downward with its familiar 8 meters per second squared. This feels normal, expected, safe. Scenario 2. Your elevator is actually in the vast emptiness of space, billions of miles from any gravitational field. But something is accelerating the entire elevator upward at exactly 8 meters per second squared. The floor rushes up to meet your feet, creating the exact same pressure you feel as weight. Do you understand what this means? It means that what you call gravity might not be a force at all. It might be acceleration in disguise. But wait, let me make this even more disturbing. Now imagine the opposite situation. You're in the same elevator, but this time you feel weightless. You float freely. Your pen hovers in midair when you release it. Water forms perfect spheres rather than falling. Again, I can give you two explanations that feel identical. Scenario 1. Your elevator is in free fall toward Earth. You and everything inside are falling at the same rate, so you feel no force between you and the floor. You're weightless because you're falling. Scenario 2. Your elevator is floating in the emptiness of deep space, far from any gravitational influence. You're weightless because there is no gravity. Can you feel the ground shifting beneath your feet? The very foundation of what you thought you knew about reality is crumbling. This is what I call the equivalence principle, the revolutionary idea that gravitational acceleration and mechanical acceleration are completely equivalent. You cannot perform any experiment inside your elevator to distinguish between them. But the implications made me dizzy with their scope. If gravity and acceleration are equivalent, then gravity isn't a force pulling you downward. Instead, you're always moving in a straight line through space and time. But space and time themselves are code. What you interpret as falling is actually you following the straightest possible path through curved space-time. Let me paint you a picture that will make this visceral. Imagine you're standing on the surface of Earth. You think you're motionless, but you're wrong. You are actually accelerating upward at 98 meters per second squared. The ground beneath your feet is pushing you upward, away from the natural path you would follow through curved space-time. When you drop an apple, it doesn't fall toward Earth. The apple follows its natural straight-line path through curved space-time. It's you and the Earth that are accelerating upward to meet it. I know this sounds insane. I know it contradicts every intuition you've developed since you learned to walk. But this is what the universe revealed to me through that simple elevator. The realization didn't come all at once. It took me 8 years of the most intense intellectual struggle of my life to work out the mathematical consequences. 8 years of false starts, dead ends, and moments of despair when I thought I might be losing my mind. I remember one particularly dark night in 1915, sitting in my study with pages of calculations scattered around me like fallen leaves. My wife Mileva had long since gone to bed, but I couldn't sleep. The numbers weren't cooperating. Every time I thought I had found the right equation, it would lead to contradictions or impossibilities. The key insight came when I realized that I needed to abandon the comfortable flatness of space and time. If gravity was equivalent to acceleration, then the presence of mass and energy had to curve the very fabric of space-time itself. Think of it this way. Imagine a stretched rubber sheet. If you place a heavy ball in the center, it creates a depression, a curvature in the sheet. Now roll a smaller ball nearby. It doesn't fall toward the larger ball because of some mysterious force. It simply follows the curved path created by the depression. This is how planets orbit the sun. This is why objects fall. They're not being pulled by a force. They're following the curved paths through space-time created by mass and energy. But the elevator taught me something even more profound. It showed me that what we call reality depends entirely on your reference frame. The person inside the falling elevator experiences no gravity. For them, objects don't fall, they float. The person standing on Earth experiences constant downward acceleration. For them, objects fall with familiar regularity. Which perspective is real? The answer that emerged from my calculations was both terrifying and beautiful. They both are. Reality isn't fixed. Reality isn't absolute. Reality is relative to your reference frame. And gravity is just another manifestation of this relativity. The mathematical formulation I finally developed predicted things that seemed impossible. It said that time should slow down in stronger gravitational fields. It said that light should bend when passing near massive objects. It said that space itself should be dynamic, expanding or contracting. At first, even I doubted these predictions. They were too strange, too far removed from everyday experience. But then the tests began. In 1919, during a solar eclipse, Arthur Eddington measured the positions of stars near the sun's edge. The light from those stars had been deflected by the sun's gravitational field, exactly as my equations predicted. The deflection was tiny, barely detectable, but it was there. That was the moment the world began to take notice. But for me, the real validation had come years earlier, in the quiet of my study, when the mathematics finally clicked into place, and I saw that the elevator had been right all along. Since then, every test has confirmed what that simple thought experiment revealed. GPS satellites must account for gravitational time dilation, or they would be off by miles. We've detected gravitational waves, ripples in space-time itself, spreading out from colliding black holes billions of light years away. We've photographed black holes, regions where space-time is so curved that not even light can escape. All of this traces back to that elevator. All of it emerged from asking a simple question. What would it feel like if I couldn't tell whether I was falling or standing still? But here's what still keeps me awake at night. Decades after that first insight, if gravity is just curved space-time, what does that say about the nature of reality itself? Everything you've ever experienced, every step you've taken, every object you've dropped, every moment you felt the solid ground beneath your feet, all of it has been your interpretation of moving through curved four-dimensional space-time. You've never actually felt a force called gravity. You've been feeling the curvature of reality itself. The elevator broke physics because it forced us to abandon our most basic assumptions about space, time, and force. It revealed that the universe is far stranger, far more fluid, and far more beautiful than we had ever imagined. And perhaps most disturbing of all, it showed us that our everyday experience of reality is just one perspective among many. No more real than the perspective of someone falling freely through space, feeling no gravity at all. The next time you feel your feet on the ground, remember this: you might not be standing still in a gravitational field. You might be accelerating upward through curved spacetime, following a path determined by the mass and energy that surrounds you. The elevator is still with us. We're still inside it, and we still can't tell whether we're falling or standing still. This thought experiment didn't just change physics, it revealed that the universe itself is a thought experiment, and we are both the observers and the observed, forever trapped in our own reference frames, forever trying to understand a reality that shifts with our perspective. That's what I learned from a simple elevator. That's what broke physics and rebuilt it into something far more profound. The question now is, what will you do with this knowledge? How will you see the world differently when you realize that everything you've called real is just your local perspective on a vast, curved, dynamic space-time? But let me show you something even more mind-bending, something that will make you question every moment you've ever lived. Remember that feeling when you're in a fast-rising elevator and your stomach seems to drop? That moment of disorientation when the elevator suddenly accelerates? What you're feeling is the equivalence principle in action. Your body is trying to maintain its natural straight-line path through space-time, but the elevator floor is accelerating upward, creating that familiar sensation of weight. Now imagine this. What if I told you that this feeling, this exact sensation, is identical to what you experience every single second of every day when you think you're just standing still on Earth? The floor beneath your feet right now is accelerating upward at 98 meters per second squared. You are constantly being pushed away from your natural path through space-time. That's what you call feeling gravity. But here's where it gets truly terrifying and beautiful. Einstein's elevator revealed that free fall, that moment when you're weightless in a dropping elevator, is actually the most natural state in the universe. When you're falling, you're not fighting against anything. You're following the curvature of space-time itself, moving along what we call a geodesic, the straightest possible line through curved four-dimensional reality. Standing still is the unnatural state. Standing still requires constant acceleration to fight against your natural motion through curved space-time. Let me take you deeper into this rabbit hole. The mathematics that emerged from this simple thought experiment predicted something that made even me uncomfortable. Time itself should be affected by gravity. Not metaphorically, not approximately, literally. Clocks should tick slower in stronger gravitational fields. I remember the night I first derived this prediction. It was winter 1907, and my small apartment was barely heated. I could see my breath in the cold air as I worked by candlelight, my fingers numb as they gripped the pencil. The calculations seemed to be leading me somewhere impossible. If gravity and acceleration were truly equivalent, and if acceleration affected time, as I had shown in special relativity, then gravity must also affect time. A clock sitting on your desk should tick slightly slower than an identical clock held above your head. The difference is tiny, undetectable in everyday life, but it's real, measurable. Your head is aging slightly faster than your feet. This isn't science fiction. This isn't metaphor. GPS satellites orbit Earth at high altitude where gravity is weaker, and their clocks tick faster than clocks on the surface by about 38 microseconds per day. If we didn't account for this time dilation, GPS would be useless within hours. Every time you use GPS to navigate, you're relying on technology that must account for the curvature of space-time revealed by my elevator thought experiment. But the implications go far beyond navigation. They reach into the very heart of what it means to exist in this universe. Consider black holes, regions of space-time so curved that nothing, not even light, can escape. Near the event horizon of a black hole, time slows to a crawl compared to distant observers. An astronaut falling toward a black hole would experience time normally, but to someone watching from far away, the astronaut would appear to slow down, their movements becoming more and more sluggish until they seemed frozen at the event horizon. Who experiences the real flow of time, the falling astronaut or the distant observer? The answer, as always with relativity, is both. Time is not absolute. There is no universal clock ticking away somewhere in the cosmos. Time is relative to your reference frame, and gravity, the curvature of space-time, affects that frame in fundamental ways. This revelation didn't come easily. I fought against it for months, looking for errors in my mathematics, hoping to find that I had made some basic mistake. The idea that time itself could be flexible seemed too radical, too divorced from human experience. But the equations were relentless. They demanded that I accept a universe far stranger than anything I had imagined. And then came an even more shocking prediction. If space-time could be curved by mass and energy, if it was dynamic rather than fixed, then space-time itself should be able to move, to ripple, to carry waves. Gravitational waves, distortions in the fabric of space-time itself, spreading outward at the speed of light from accelerating masses. When I first calculated their existence, I thought they would be far too weak to ever detect. They seemed like mathematical curiosities, interesting in theory but irrelevant to observation. I was wrong. In 2015, more than a century after my elevator dream, scientists using laser interferometers detected gravitational waves from two black holes colliding 1.3 billion light-years away. The ripples in space-time that reached Earth were incredibly tiny, smaller than 1/10,000, the width of a proton. But they were there. The detectors heard the universe itself ringing like a bell, carrying information about the most violent events in the cosmos directly to us through the curvature of space-time. All of this, GPS satellites, gravitational waves, black holes, time dilation, all of it traces back to that simple elevator. All of it emerged from asking what it would feel like if you couldn't distinguish between acceleration and gravity. The elevator didn't just change how we think about gravity. It revealed that the entire universe is made of geometry. Mass and energy tell spacetime how to curve. Curved spacetime tells matter how to move. That's the entire universe, described in 2 sentences. You are not a collection of particles held together by forces. You are a pattern in curved spacetime, a temporary organization of geometry that has learned to think about itself. The elevator revealed that we live in a universe where space and time are unified, where geometry is physics, where your experience of reality depends on your motion through dimensions you can't directly perceive. This isn't just abstract theory. This affects your daily life in ways you never realized. That heavy feeling you get when you wake up in the morning, that's your body adjusting to the acceleration imposed by Earth's curved space-time. The way water swirls down a drain, that's the Coriolis effect, a consequence of your motion through curved space-time as Earth rotates. The GPS in your car, it's constantly calculating corrections for gravitational time dilation. You are living inside Einstein's elevator every moment of your life. You just never realized it. The elevator broke physics because it forced us to confront the possibility that reality itself is relative. Not just our measurements, but reality itself. What you call up might be meaningless to someone in freefall. What you call real might be just one valid perspective among infinite others. This is the gift of the elevator. It taught us humility. It showed us that the universe is far vast, far stranger, and far more beautiful than our human-scale intuitions could ever grasp. But it also taught us something else, that the act of thinking about these questions, of using our minds to transcend our limited perspective, is perhaps the most remarkable phenomenon in the known universe. You are curved spacetime that has learned to contemplate its own curvature. You are geometry that has awakened to its own existence. You are the universe trying to understand itself. The elevator is still there, waiting in your imagination. Every time you wonder about the nature of reality, every time you question your assumptions about space and time and gravity, you step inside it again. And each time it offers you the same choice: accept the comfortable illusion that your perspective is absolute and real, or embrace the vertigo-inducing truth that reality is far stranger and more wonderful than you ever dared to imagine. The elevator broke physics, but in doing so it revealed something infinitely more precious, a universe worthy of wonder, mystery worthy of a lifetime of contemplation, and a reality so beautiful that even its strangeness is a gift. What will you do with this gift? How will you see yourself differently when you realize you're not standing on solid ground, but accelerating through curved space-time? How will you treat others when you understand that their perspective on reality is as valid as your own? The elevator is waiting. The universe is waiting. And somewhere in the curvature of space-time, the answer is already written, ready for you to discover it. Step inside, feel your feet on the floor, and ask yourself, am I falling or am I standing still? The answer will change everything.